Hey, been 8.3, some partial fractions. Go ahead and raise this up a little bit here. Here's the gist. The idea is you have two fractions with different denominators. So what we do with the fractions is we try to add them together by getting common denominator, least common denominator. So we multiply one fraction essentially by the denominator of the other fraction, top and bottom, and vice versa. So this one we multiply by x plus 3. The second one multiply by the first fraction by x plus 4 over x plus 4. The second fraction by x plus 3 over x plus 3. When you multiply, again, I'm not going to do distribution yet. The idea is to get the same denominator, so it's the product. The two products are the same. So put it as one fraction. So once you get to this point, then the idea is kind of simplify. So now I'm going to distribute, and then I'm going to combine like terms. And so you end up with 7x plus 23 over these two parentheses or two products. You can fold it out if you want and make it look like this. So either way is fine. This would be to simplify the fraction. Kind of put it together as one big fraction. Now, partial fractions are a little bit different. Partial fractions begin here. This is the starting point. So if we want to do what's called decomposition, partial fractions, the idea is starting here or here and working your way all the way back and figure out what two smaller fractions added up to this one, or what three fractions, or what four fractions, etc., etc. We're going to take a fraction that's kind of already like at the end of the stage, and we're going to figure out what were the smaller fractions that got us to that point. What were the smaller fractions that were added to get to this point? So here's the gist. Find the partial fraction decomposition for each of the following, and then we're going to solve for what are called constants. So if I take a similar fraction to this one, not the same one, but the idea is whatever's in the denominator, whatever you can factor everything out as much as you can. So this one will factor in x minus 3x plus 1, because negative 3 times positive 1 is negative 3, and it also adds up to negative 2. So because now this essentially was from two linear factors, being first power, see, we work our way back here. It was here at 2. Notice that each one of them had its own little fraction. That's where it came from. So it was a product to get you that. So essentially, we're trying to figure out if it's a 2 and a 5, what are these numbers? So we use variables. So we use what are called constants. Well, it's like a variable because you don't know what they are, but we call them constants. So I'm going to use a constant to have, so there's two parentheses here. So I'm going to use one constant for one and one constant for the other. So we're going to separate it into two smaller fractions. The idea is to figure out what are those a values. So once we have this point, it's kind of like this point. You're back to here, except instead of a 2 and a 5, it's an a and a b. So you're still going to try to do the same thing. You're still going to multiply to get the same denominator, so you get the same fraction. So that's the gist. So the x minus 3, I'm going to multiply by x plus 1 over x plus 1. The x plus 1, I'm going to multiply by x minus 3 over x minus 3. And so I'm going to have those two fractions with the same denominator now. I'm going to put it as one fraction. Again, this step is like over here before I distribute it. So I'm at this point. But now this fraction that I simplified is equal to the fraction that I began over here with. So these two are equal. So because you have two fractions that are equal, the idea is because the bottoms match, the denominators match, and these fractions are the same, it forces the numerators to be equal. So the idea is once you simplify the right-hand side, set the top equal to the top and solve for x. So the idea here is the bottom kind of fizzles out because they're equal. So the top equals to the top. So you're set with this part here, and you're going to essentially try to solve for x. So we're going to work it in this fashion. So as it is, the idea is to click, because we have two constants that we're looking for a and b. We're going to try to pick two x values at random to see if we can find those a and b values. We're not going to solve for x. We're going to solve for a and b. So we're going to choose x in such a way that's going to isolate b. In other words, it's going to cancel this out, because if you can pick a -1 here, notice that this is going to be 0. So the idea is to kind of pick something for x here that's going to cancel this out. So I can solve for b. And over here, I'm going to pick something for b, for x, so that the b cancels, so that this becomes 0. So we're trying to isolate one at a time. That's what we're doing. So I'm going to pick two values that kill one, essentially cancel one of the letters. So if I pick -1, I plug -1 here, -1 here, -1 here for x. Notice that a disappears because 0 times anything is 0. This is -4. This is -8. So -8 equals to 4b. Just solve for b very quickly by dividing by -4. When x is 3, plug in a 3 for everything. B cancels. B goes bye-bye. And so 4a equals to 12. And so you divide both sides by 4, and a is 3. So now we have the values for a and b. So a is 3 and b is 2. So these must be the two fractions that we began with. This is called partial fraction decomposition. And the idea, essentially, of picking these values so that things cancel, this is called the Heaviside method. There are two methods that I'm going to really, or refocusing on, but mostly this method. Heaviside method is you pick x values that isolate one of the variables. You're trying to cancel the other ones out. So you're trying to make one side heavy so it disappears, essentially. And then we're going to talk about just brute force, just kind of multiplying everything across, but we'll do that in a while. So this is ultimately your answer, the partial fraction decomposition. So now, as we go to the next one, you see this one has 3 x's, essentially. Again, where they're what are called linear factors. They are x to the first powers. So this must have come from 3 fractions, one with x by itself, one with x plus 1, and one with x minus 1. So over these x's, x plus 1, x minus 1, we're going to use letters of the alphabet. So capital A, capital B, capital C. And again, I should have specified that here. You start with the consonants that you pick are capital letters, and you typically start with the alphabet, A, B, and then C, D. You might have so many fractions that you need. You just keep going. So now this one has 3 fractions. So notice that 1 fraction for each linear factor with a constant for its numerator. So each fraction that has x to the first and the bottom, or a linear factor, gets a constant, capital letters. And so now here's the gist. I kind of skipped some steps here, but you understand that to get this, I want this to look like this. So ultimately, I want them to match. So I know what I need to do ahead of time. So the denominator has x here. I want to get an x plus 1, an x minus 1. So I want to skip some steps here and say, well, what's missing? What's missing? What did I put on the bottom here so that this becomes all of that? Well, it must be the 2 parentheses that were not here, so I put them in there. So essentially what I did to the bottom, I do to the top. This one is missing a factor of x and a factor of x minus 1. That's what I added on to this part. So I put to the top. So what you do to the bottom, you do to the top. This one's missing an x and an x plus 1. See? The C? That's what I added to the bottom, or multiplied to the bottom. So that's what I'm multiplying to the top. And so skipping a step where I just put it all together as one fraction. Make it a little less work, make it a little easier. So now that this is in the bottom matching, the top is equal to the top. So we scratch out the bottom, just gonna work on the top. So you understand here I have x plus 1, x minus 1. So if I have x plus 1, if I choose -1, that will cancel and make a 0. If I choose x equals to +1, that will cancel and make it a 0. And then over here I have just x by itself. So if I pick x to be 0, that will cancel this. If you pick in x values, they're going to cancel some of these factors. So if you pick x to be -1, plug it in for -1. In other words, plug in -1 everywhere. In particular here, -1 plus 1 is 0. 0 times all of that is just 0. So A is done. Over here, another x plus 1. So you put a -1 here. You see C is 0. So ultimately, C is gone. And so you have just A and C are gone. So all you have there is B. So -1 minus 1 is -2. -2 times the -1 is a +2. So this is 2b. And then over here, this is 4 times -1 squared is +1 times 4 is 4. 2 negatives at composite. So 4 plus 1 is 5, minus 15 is -10. So -10 equals to 2b. And now you divide both sides by 2, and you solve for b. Now we have the answer for B. Now when we pick x equals to positive 1, put it all into the x's here, notice that here, these two disappear because you have 1 minus 1. So A and B both disappear, essentially. So you just get C by itself. So 1 plus 1 is 2. 2 times 1 is also 2. So 2C here, this is 4 minus 1 is 3. 3 minus 15 is negative 12. Divide both sides by 2. C is negative 6. And same thing for the third one here. Plug x will be 0. These two guys that have x's, 0 times all of that, 0 times b, 0 times c, kind of annihilates it. So it just puts the a by itself. So 0 plus 1 is 1. 0 minus 1 is negative 1. 1 times negative 1 is negative 1. So this is negative 1a, or just negative a. This is negative 15. So divide both sides by negative 1. Essentially, a is positive 15. So a is 15. B is negative 5. And C is negative 6. So this is your partial fraction decomposition. Or because you're adding negatives, you can make these into minuses. Either way is fine. So that's how this works. Again, this is what's called the Heaviside method. Okay, so let's try another one here. This is the idea of what's called a repeated linear factor. So now x plus 2 is linear, but there's a square there. The idea essentially is, how do you say, you want to get one factor for x plus 2. However, this is squared, so we need every power leading up to the second power. So you have x plus 1 for this one, x plus 2 to the first, and now x plus 2 to the second. Had this been a third power, it would be x plus 1, then it would be x plus 2 to the first, x plus 2 to the second, x plus 2 to the third. Whatever power is out here, that we need one for each of the powers leading up to it. So let's say this was a fifth power. You would have x plus 2 squared, x plus 2 to the third, x plus 2 to the fourth, x plus 2 to the fifth. Every power leading up to it because they're all factors. Okay, so now this actually becomes three fractions. So so now we want to turn all of this into this denominator. So my next step is to write everything as one fraction where this denominator matches that denominator. So it kind of tells you what to do here. So x plus 1, what was attached to it to make it all of this? I did x plus 2 squared. X plus 2, what was attached to make it all of this? I added a factor of x plus 1, or multiply a factor of x plus 1, and then another factor of x plus 2 to make it squared. This one already has x plus 2 squared, so I added a factor or multiplied a factor of x plus 1. So now we set the top equal to the top, and we solve for x. So in essence, now here x plus 2, so I choose x minus negative 2, and over here x plus 1, so I choose x equals to negative 1. So at this point I only have two values. So I'm going to try it. If I plug in negative 2, a and b cancel, and then so c survives, so you have negative 1c or negative c equals to 4, negative 4. Then dividing both sides by negative 1 will kill the negative there. And so c is equal to 4. So now when x is negative 1, the left side is negative 2. The b and the c cancel because here and here go away. And so it's negative 1 plus 2 is a positive 1. 1 squared is 1, so this is just 1a. So a is negative 2. So you have two values here, but now you understand that there's nothing else I could pick for x that's going to make anything on the right-hand side equal to 0. So at this point, you pick any third value you want that's different from these two. So for simplicity, I pick 0 because it's an easy number to deal with. You could pick 7, negative 12, 2 million, whatever you want. So if I put a 0 here, nothing cancels. Notice how all the letters survive. So 0 equals 4a plus 2b plus c. So you look at this and say, well, I don't really have one letter I can get the answer for. However, you have a to equal negative 2 already, and you have c to equal 4. So you know what these two are equal to. Plug 4 in for c, plug negative 2 in for a, and solve for b. So that's what I did here. I moved things around, and I got b to equal to 2. So that's how you find b. So now that you have a, b, and c, a is negative 2, b is positive 2, and c is positive 4. And this is your partial fraction decomposition, and this is what's called the Heaviside method, as we're solving for what are called constants. And that's how this works. So let me have a couple more here involved. I have another one or two here. This one's are a little longer because they have what are called irreducible quadratics. A quadratic is a second power of x inside the parentheses that you cannot factor any further. So x squared plus 2 is what's called an irreducible quadratic. Now this guy, because the second power you cannot reduce, you cannot factor it, we have to do a first power. So we use the idea of y equals mx plus b. So this is like mx plus b up here. But instead of m and b, it's the next letters that are available. So I have one fraction for x plus 1, and then this becomes bx plus c on top. This is a quadratic factor that you cannot simplify or cannot factor, what's called irreducible. And so you use a linear factor on top. Always one power less than the bottom. So I make one fraction where this 2 now becomes that denominator. So x plus 1 is missing x squared plus 2, so that's what I put on top. X squared plus 2 is missing x plus 1, so that's what I throw on top. So now the denominators are the same, so the top equals to the top. Now, the only problem here is this. Essentially, I only have one number for x I can plug in to make one of them 0. I can't do anything here because if I could pick an x value and make the 0, then this would be factorable. It would not be irreducible. So I have to be worried about that. But I can plug in -1 here. So -1, plug it in, -1, all this stuff cancel over here on the right. And so you have a to equal 1/3, or 3a to equal -1. And then divide both sides by 3 to cancel the a, to cancel the 3's to get a by itself. So we get a to equal -1/3. Now the problem is I can't pick anything else here that's going to make this 0. So I'm going to have a mess here. And now you look at it and say, well, what you did, and then again, on top of that, I have a fraction I have to put in here. It's going to make this horrible. So my only alternative here is to multiply everything out. So typically when we have irreducible quadratics, we have to multiply, or we have to solve by multiplying out everything and setting the system, what's called a system of linear equations. In other words, we have multiple unknowns. So I'm going to take this whole thing. Essentially, I'm going to distribute to ax squared plus 2a. Then I'm going to essentially what's called FOIL. I'm going to multiply all this out. You get bx squared plus bx plus cx plus c. And then I'm going to combine the like terms. So you see how these both have x squared? I'm going to factor x squared out of it and have a plus b left. These two have x's. I'm going to factor out the x and have b plus c. These two have nothing, no x's. So I group them together. So I look at the original problem and say, well, that equals to 2x plus 1. So if these two things are equal, whatever's in front of x on this side has to be whatever's in front of x on this side. Whatever is equal to just a constant has to be whatever equals to a constant here. And whatever's in front of x squared over here on the left have to equal whatever's in front of x squared on the right. So there is no x squared, so I put a 0 there in its place. So because I want them to match up a power for power. So therefore, a plus b has to equal to 0. B plus c has to equal to 2. And then 2a plus c has to equal to 1. So normally I'd have to multiply things to cancel with a b or to cancel with a and kind of work my way through. But since we did this important step over here, we now have an answer for a. So I'm going to plug in a to equal -1/3 here. So -1/3 plus b equals 0. But now all you do is add 1/3 to both sides. So now I have b. So now I have a and b. So now over here I know that b plus c equals to 2. B is 1/3. So 1/3 plus c equals to 2. Now when I take away 1/3 from both sides, this is over 1. I have to get common denominators. So I multiply this guy by 3/3. So this is 6/3 minus 1/3, which is 5/3, or 5/3, which is what this is. Okay, so that's how I'm getting 5/3 there. So now A, B, and C are all fractions. So I go back here and I say, okay, I'm going to put this all back. I'm going to put this all back here. So A is negative 1/3, B is positive 1/3, and C is positive 5/3. So as I do that, I don't want this to be a fraction on top of a fraction. So this 3 joins the bottom of the fraction. So it's negative 1/3. This one, they both have a 3 on the bottom. So I'm going to factor out the 1/3, leaving just x plus 5. And this 3 will join the bottom. And this is what's called partial fraction decomposition. This is not the, it's a little bit of the heavy side method here, but ultimately just kind of brute force, just kind of multiplying everything out. So there's your starting point and there's your ending point. This thing took my whole page here, my whole notebook page. Just to let you know, it take a while. And again, just doing another one similarly. And this one has 2x squared plus 1, which is also irreducible. But it's a quadratic and it's a square. So the x, I get a because it's linear. I put a constant. Now this one is a second power. I have to respect the first power of it and the second power of it. So whatever power this is, I have to respect one for each power leading up to it. Because these are irreducible, they get y equals mx plus, or mx plus b. So this should be mx plus b, but we can't do m and b no more. We do the next letter available. So bx plus c. Then dx plus e. So this will be the setup. So now I want everything to have the same denominator as the bottom here. So x is missing 2x squared plus 1 squared. Bx plus c is missing one of these 2x squared plus 1, but also missing an x. The dx plus e is only missing x. So the top equals to the top. Again, get rid of the bottom. Now I can plug in, because there's x here and x here, I can plug in x to be 0 and solve for one of the letters. I can do that to help me, make it a little easier. So I plug in a 0 for all the x's. B, C, D, and E all cancel. A survives, so A is equal to negative 1. However, the other letters, you can't really plug in anything because you can have a linear system, but it's not going to really help you. So at this point, I'm going to take the original and I'm going to multiply it all out. So this part, if it's squared, it means two parentheses are the same thing. So when you multiply it all out and you simplify, you get this result. Here, I multiplied the x into this parenthesis, so bx squared plus cx. And here I multiplied the x into both of these. So now here I distribute the a into all of this, 4ax to the fourth, 4ax squared plus a. Here I'm going to FOIL all of this out, so I have what here, 2b, x to the fourth, bx squared, 2cx to the third, and then cx. I made a little mistake here. You saw a little while ago just e by itself. This is actually, instead of, this was a c here. It's actually cx. I just caught that. So dx squared plus e. So now, after all is said and done here on the left, I only have 3x minus 1. But on the right, I have fourth power, I have third power, I have second power, I have fourth power all the way down. So I'm gonna take the 4a and the b, the 2b, and I'm gonna factor x to the fourth from it. I'm gonna take my 2c to the third by itself, 2cx to the third. Then I'm gonna take my x squared, d and b here, b plus d x squared, and then plus a over here. These three, the arrows. Then c plus ex. They both have an x here. That was a mistake I had right there, but I fixed it. So c plus ex, and then plus a. But on the left side, I have to have constant. First, I have x to the first, x squared, x to the third, x to the fourth. So I only go up to x to the first. So I bring in zeros for the higher power. So 0x squared, 0x to the third, 0x to the fourth. So in essence, 4a plus 2b equals to 0. So in this case, I have this first. I'm going to start with the first equation before I move on. Remember that I already had a to equal negative 1. So if I plug in a to be negative 1, then b, when you follow this logic, or when you follow the equation, b has to equal to 2. So now I have a and b. So now here it says that 2c equals to 2c equals to 0. So again, that comes from 2c equals to 0. Divide both sides by 2. There's your c value. So because whatever's in front of x to the third over here, which is 2c, has to be whatever's in front of x to the third over here, which is 0. So now c is 0. So now we have a, b, and c. So now we go with the next one. 4a plus b plus d is in front of x squared on the right. Over here, 0 is in front of x squared on the left. So these two things have to be equal. But because I already know a to be -1, and I know b to be 2, I plug that into the equation. So -2 plus d equals to 0, so d is 2. So that's pretty good. Now, it kind of works out like this in this time. It doesn't always work out that way. But now c plus e equals to 3, because they're both in front of the x over here. So if c plus e equals to 3, but c is 0, then e must equal to 3. And the last one reiterates, kind of tells me what, actually I didn't have to, in retrospect, I didn't really have to do this, because the last one, lucky enough, a is equal to -1, which I already knew, but then I would take this answer and I could plug it here and then work my way down if I wanted. Since I did it ahead of time, sometimes you get it, sometimes it helps you, sometimes it kind of reiterates. Sometimes you get to the same answer, but nonetheless, these are your values: A, B, C, D, and E. So A, B, C, D, E, I'm going to put A to be -1, B to be 2, C to be 0, D to be 2, and E to be 3. This thing plus 0 kind of gets rid of it, so that's gone. So -1x plus 2x over 2x squared plus 1 plus 2x plus 3 over 2x squared plus 1 squared. Look at that mess. That's how these work. And now one last problem here. Or maybe, yeah, one last problem here with partial fractions. The whole time I did it to where the highest power on the top is less than the highest power on the bottom. But every once in a while, or sometimes, you get where the highest power on top is bigger than the bottom. So the numerator, if it has a degree that's greater than or equal to the degree of the denominator, in other words, if the top has a higher power than the bottom or the same power, you have to divide everything. So this is long division. This is a college algebra idea, or division. So I'm going to take x to the third times what makes 2x to the fourth. Well, I need another x, and I need a 2 here. So now we'll distribute the 2. This will be positive 2x to the fourth, and this will be negative 8x squared. However, because we're dividing and subtracting, these two signs have to change. So positive 2x to the fourth and negative 8x squared, you have to change the signs. That becomes negative. So here, let me add that there. Change the signs. Okay, because you're subtracting. So now this cancels and this cancels actually. So the only thing that's left is 5x minus 2. Notice that this remainder is a lower power than the what you're dividing by, what's called the divisor, excuse me. So this is your remainder. So when you divide this out, you get 2x as the quotient plus 5x minus 2 over this fraction, or over this denominator, x to the third minus 4x. So here's the problem. Here's the issue. This part has already been decomposed, so to speak. It's already been divided. We have to do the partial fraction decomposition of the remainder. So here, this is essentially x to the third minus 4x. So I look at that and say, well, look, they share an x in common. So I'm going to factor an x out, leaving x squared minus 4. But now this can be factored as it's a difference of squares into x minus 2x plus 2. So this part, I have to do everything we did earlier in this section. So I do this. They're all linear factors, so a, b, and c. I get the common denominator, and I get what's missing. So the top equal to the top. Because these are linear factors, I can do the Heaviside method. So I'll leave it to you to read through that. But the idea is I pick x equals 2 to cancel this one, x equals -2 to cancel out this one, and x equals 0 to cancel out this one. In doing so, I solve for b, c, and a respectively. So I now have my answers for a, which is 1/2, and then b is positive 1 and -1 for c. So over here, this is 1/2 over x, which is really 1 over 2x. B is what? Positive 1. And then C is -1. This one was from the beginning. So 2x plus all the answers we just got. So the partial fraction decomposition is 2x plus all of this fraction decomposition. This is the partial fraction decomposition for this fraction. Now, this only if the top power is greater than or equal to the bottom power. You have to actually divide. I'm gonna probably do it on the software or on the homework and the quiz and the test where the power on top is less. So you can do this methods again. These what we've been doing instead of doing long division. Just kind of work this out because sometimes I teach it, sometimes I don't in my algebra classes. So some of you know how to do long division, some of you don't. But nonetheless, this puts us through the end of 8.2.